Now let's talk about an important topic, which is functions. We will be talking about functions a lot in machine learning, so it's important to get some concepts out of the way. So function is a mapping. So let's say there's a function f. It's a mapping from set x to set y. So in the sense that if you have x belonging to x, right, and you take f of x, it will map to a unique value y, right? So uh, what that means is that this mapping can be many to one, but it cannot be one to many. So to take a particular example, so x f of x could be, for example, ax square plus bx plus c, which is a parabola. It could be opening downwards, it could be opening upwards, but it is a parabola, x and y, right? And for any value of x, you get a unique value of y, right? Compare that to ax square plus by square is equal to c square, right? So in this case you will get an ellipse, right? And here one value of x can map to like two values of y, so this is not a function. So now let's talk about continuity and differentiability of functions. It's good to get those concepts of smoothness and differentiability out of the way. So continuity of a function, as you know, is defined that if for every x, so let's say x is a continuous variable, right? So x is a continuous variable. Then limit delta x tending to 0, f of x plus delta x is equal to f of x. So that's one definition of continuity. We also talk about smoothness of functions in addition to continuity, and usually this smoothness is defined as uh, that the function should not have too many kinks. So let's take example of a few functions. So let's say we have some axes. Let's draw some axes, and then now let's draw some functions. So if we have a function like this, right, you can see that there's a discontinuity here. Okay, because here if we take the limit of x and x plus delta x, you can see that that limit will not be f of x in this narrow region as delta x goes to 0, whereas a continuous function could be, for example, like this, right? So here this is continuous, but we see that there's a sharp corner here. So this is not smooth, the function is not smooth. Whereas a function that is defined by a quadratic equation is smooth. So this is smooth and continuous. Right, so here what is this definition of smoothness? How do we characterize these sharp corners or the lack thereof? For that we have to go to differentiability, but before that let's talk about slightly stronger definition of continuity, and that is something called Lipschitz continuity. So a function is Lipschitz continuous if you take 2 points, right? So we take f of x1, right, minus f of x2. This is the mod of this is less than or equal to k times, for some constant k, x1 minus x2. So think about this. What does this mean? So what this means is that I'm defining, let's draw some axes. Okay, and let's draw a function. Okay, and then let's draw a cone around it. Oops. Okay, so at any point let's draw a cone. Okay, so what is the so what are these basically what is the slope of this cone? The slope of this cone is minus k or plus k. Okay, so the function will always lie inside the cone. So in this region, in this shaded region, the function will always lie in the shaded region, and this constant exists. So this doesn't have to be an infinite number. As long as this constant is finite and everything is lying within that cone, then the function is Lipschitz continuous. And why is that important? We will, this idea of continuity or smoothness, uh, continuity and smoothness are very very useful in machine learning when we will look at how to cut spaces of different features that define your sample points, and how to define boundaries on those features, or the behavior of models on those features. So keep this in mind. This is Lipschitz continuity. So to give you some examples, let's say if we have a function which is y is equal to x square, right? You can see that this x square rises very fast for large values of x or large negative values of x, so it will violate any constant k after some point, right? So the um, derivative of this function itself is proportional to x. So when x becomes very large or very small, then it will go out of any cone of size of slope k or minus k. uh, Similarly, if you look at y is equal to square root of x, then near 0 you will have an infinite derivative. So around that point it will not be Lipschitz continuous. Okay, but on the other hand, if you take functions such as y is equal to sine of x, right, then it is Lipschitz continuous, because derivatives will never exceed plus and minus 1, and because of that you can define k, your k can be 1, and the function will always be contained in that cone. Now let's talk about derivatives of a function. So derivative of a function, for example, is as you already know, is the slope of the function. So let's say you have a function f of x, right? And let's say it looks like, let's take the example of the quadratic function. Right? So this is ax square plus bx plus c. So for this function, the derivative we will define as f dash of x, and then we know what the derivative is, which is equal to 2ax plus b. Right? So that's how we define the derivative. Now, as long as this derivative is well defined, then the function is smooth, right? So this derivative has to exist for all x, and it has to be a finite number, right? So there are examples where the derivative will not exist. So for example, when the function is discontinuous, then the derivative will not exist. There are examples of functions that are continuous but the derivative may not exist. Okay, so let's take an example. where your function is like this. Let's say mod of x. So this is your function mod of x. F of x is equal to mod of x. So for this function, the derivative exists pretty much everywhere except at the origin. So when x is less than 0, f dash x is minus 1. Okay. Minus 1 if x is less than 0, and plus 1 if x is greater than 0. Now for these functions, what is important, right? So we can also call the derivative as gradient. So for these functions, there's another concept that is important to define, which is called subgradient. So you can imagine that there is actually a tangential line, right? What does a gradient define? That defines a tangential line. So for example, if you are looking at the gradient here, it's a slope of this tangential line. Here it is the slope of this tangential line. So here, if we draw a tangential line, now we know that this tangential line, we cannot precisely define it because there are several possible answers. But we do know that this tangential line cannot go above this and it cannot go above this, right? It has to slope below them. So it has to stay below them. So for such kind of points, we say that the subgradient exists, whereas the gradient may not exist. So for this important class of functions, this subderivative or subgradient exists, right? So what is that important class of functions? It is set of convex functions. This is another important concept that you should know. So what is a convex function? Convex function is a function where if you take any 2 points and you join a line, the entire function between those 2 points lies below that line, below that chord. Okay. So formally you can define it as that your let's say if you have a scalar lambda that belongs to 0 1, then if you have lambda times f of x1 plus 1 minus lambda times f of x2, right? So that is basically any point on this line, it is going to be greater than equal to uh, f of lambda times x1 plus 1 minus lambda times x2, right? So if you take any if you take like any linearly interpolated point here and you go down to the interpolated point, so let's say this is x1, right? This is x2. Then this f of a point between x1 and x2 is going to be below the line, below the point that is on this line that is connecting the 2 points, right? So that's a convex function. So for convex functions, and these convex functions uh, need not be smooth. So for example, this uh, fx is equal to x mod of x is a convex function. You can draw any chord and the function will lie below that. So here at certain points such as this point, there's a left derivative and a right derivative, right? So you can take the limit from the left or the limit from the right. So if you take these uh, these are called subtangents, these lines that graze this point, their slope is going to be between those two slopes. Okay. So the slopes are called subderivatives or subgradients. Subderivatives. And these are slopes of subtangents. In addition to that, now that you can define the derivative of a function, we should also know what are critical points of a function. So if you have a function f of x and you take its derivative, right? If you set its derivative to be 0, right, so then the values of x that give you this particular derivative to be equal to 0, those are going to be critical points of that function. So again, let's take the example of a square of a quadratic function, right? So let's say ax square plus bx plus c, right? So this is the function, this is f of x. Now let's see what f dash of x looks like. Right, so f dash of x is going to be 2ax plus b, and if we set it to 0, that means x is equal to uh, minus b by 2a. So this is the point where the derivative is 0. Okay, so and you can see that the derivative is negative here and positive here. So this uh, the 2ax plus b equal to 0, that is going to look like a line like this, right? So the derivative is negative on the left side of this point and positive on the right side, and is 0 exactly at this critical point. So now these critical points can be maximas or minimas, okay, or they can be points of inflection. In higher dimensions, these can be saddle points also. So how do we know that whether it's a maxima or a minima? So for that we have to go to the second derivative, f double dash of x. In this particular case, it's going to be 2a, right? So we can see that if a is positive or a is negative, we have two different behaviors. So here a is greater than 0, and for that we get a convex function, a parabola that is opening upwards. And for that uh, so basically f double dash x, let me draw that, let's take blue color, right? So that is going to be a constant. This is f double dash x, okay, and this one is f dash of x, okay. So this is going to be a constant, and if that is greater than 0, okay, then we will get a minimum if f double dash of x is greater than 0, and we'll get a maxima if f double dash of x is less than 0. And point of inflection is when we can't decide in the neighborhood of that particular point if it is neither strictly positive nor strictly negative. The second derivative of f is neither strictly positive nor strictly negative. In that case, we don't know whether it is going to be a maxima or a minima. So an example of that would be, let's say f of x is equal to x cubed. Then we have a function that looks like this. Here the derivative is 0. F dash x is equal to 3x square. We set it to 0, we'll get x equal to 0. Now if we look at f double dash of x, right, we will get 6x, which is neither strictly positive nor strictly negative around x is equal to 0, right? So it is positive on one side and it is negative on the left side and positive on the right side. So we can't really say that it is a maxima or a minima in a particular neighborhood, and therefore this is a point of inflection. It's not neither a maxima nor a minima. Coincidentally, you can also see that this particular function is not a convex function. I can join any two points, and there's no guarantee that the function will lie below that. So for convex functions, another definition, equivalent definition, is that your second derivative would always be greater than equal to 0. That follows from the function lying below below the chord. Okay, and the opposite of that is a concave function. This is for convex. For concave function, where the parabola opens downwards, right, or the function opens downwards, your f double dash of x is going to be less than equal to 0. Okay, for all x. This is for all x.